So in this video, we are going to apply the second velocity profile using UDF, and the procedure exactly same. So only difference here is that the equation is different than the velocity profile for the pipe. So for channel flow, closed channel flow, this is a velocity profile, and the maximum velocity you're going to get is 1.5 times of the average velocity. That is, if we define average velocity as 1 meter per second, so the maximum velocity you should be getting is a 1.5. Okay, so again the same thing is here. So what I'm going to do here is that I'm going to write this file. Okay, and instead of the pipe, I will put the name as channel. Okay, the first thing. And the second thing is that I will be changing the boundary conditions for the access to the wall. Okay, this will be bottom will be the wall. But the only issue now we are facing here is that, which I can easily do. The only issue here is that the grading should be done on the both sides. So that's why I have to start from the mesh file. Otherwise, very simple. So this is the channel, and this is a mesh. So hide the mesh and display pre-mesh only. And go back to the blocking, and from here select the vertical edge. And this time make the same grading on the both sides. So 0.0005, 1.1, and apply. And right click on the pre-mesh and recompute. Okay. Make sure the warp1 is not displayed. This is going to be the mesh for the channel. So both sides will be the wall. So again, you have to convert this pre-mesh to the unstructured mesh, because the previous mesh has the different mesh setting. So it should be now also replaced by the new mesh. And then in the output mesh, only thing you have to change is the boundary condition for the axis. So this should also be the wall. So you can copy the boundary condition directly from here. So copy and paste over here. Okay, and accept and output the mesh file. So yes, and again, as I told you, that you have to make it 2D, and the name is channel. Okay, done. So now what I can do here is that I can just replace the mesh file, because everything else is same. So replace the mesh file and use the channel.msh. And the one more thing is that I have to copy the velocity profile for the channel as well. So channel velocity profile is over here. This is for the closed channel. Open channel is on the bottom side. But I will not give you this velocity profile, and you have to do it yourself. Okay. So we have the working folder, which is over here. Okay, place the UDF file in the same working folder. It is very much compulsory. Okay, so now we have the same thing should be there. Material properties, just confirm. It should be the same thing. And the velocity at the inlet. Now we have to compile the new UDF. So right click here and compiled. This velocity profile is going to be for the channel. Okay. So delete this file and add a new file which is for channel. Okay, and build. Okay, so this is this has built the UDF. So just load the file, and then you have to go to the boundary conditions, and in the boundary conditions you have to select the new UDF for inlet. Okay, so this is the velocity profile for the channel. Apply and close. So you have to again initialize data from the inlet. So I will be giving the mean velocity or the average velocity, that is 1 meter per second, that is from the inlet. And then I will run the case again in a similar fashion. So I will be putting like 500 iterations and click on calculate. Okay, so we have some issue in the flow scheme. So why it is so? Okay, so let's try with the coupled. Okay, so again initialize solution. Okay, one more thing is very much important here. This is not axisymmetric case, this is a planar case. So make sure this is planar. This can be the one source of error, and here it should be the simple one, and initialize solution from the inlet. Okay, and again run the calculation. So I hope this time this should not make any problem. So I think 500 iterations are more than enough. So we can see the convergence has been achieved within the 250 or 300 iterations. You can stop here. Okay, now for the results, click on the first contours. So maximum velocity should be 1.5. This is a mistake which I made here. I should be saving the file first. Okay, anyhow, so again I will be opening the file. So Fluent, and the working folder is set, so I will choose the case and data. This is the channel, open and start. So after making any changes, please make sure that you save the file, because this thing can happen at any time. Okay, so this will load both of the files like the case and data file, and so just make sure everything is set. So properties should be 100 and 0.1, and the velocity profile and axis should not be axis. So I think that we have to replace the mesh file. Okay, so axis is now going to be the wall. Okay, what about if I start from the very beginning? So we start with the mesh file, and so mesh file is over here, channel. Okay, so very quickly I'm going to put the the model should be laminar. So it's a laminar model. Okay, and material properties I'm going to put is 100 and 0.1. Change create, and on the boundary conditions, just make sure that every boundary condition has the proper type. So axis and wall should be wall, and both should be wall. This is a pressure outlet, this is the pressure velocity inlet. So I will be putting initially I'm putting the, let's say, 1 meter per second. Okay, apply, and the methods I'm going to choose is the simple, and in the monitors I'm going to put the many zeros here. So 1 10 power minus e power minus 20, and copy this in all the fields. Okay, and initialize from the inlet. Okay, now run the calculation. Okay, make number of iterations to 500. Okay, now we can stop the simulation. So click on stop here, and so right now this is without the UDF. So I want to display the velocity contours. So it shows the maximum velocity to be 1.4, because it has not enough length to make the fully developed. So that's why it is showing in this way. So you can make it banded, and from the color map option you can make the number of layers or number of contour levels to 30, and defined by the BGR. So this looks like in this way. Okay, and second thing is that you can display the vectors, so they will show you the like this. So you can see that starting the flow is developing, and eventually it develops, but it does not give you the maximum value that should be the 1.5. Okay, so now we have to apply the UDF. So from the boundary conditions, and at the inlet, I'm going to choose a velocity profile that is the axial velocity profile. This is the UDF velocity profile pipe. No, we have to compile the new velocity profile that is for the channel. Okay, so right click here, compiled, add. This is velocity profile for the channel. So velocity profile for channel. Okay, click on build and then load. Okay, now at the inlet we have to select the appropriate type of the velocity profile. This is velocity profile for channel. Close and again run calculation. Okay, now you can check the your vector plots. And you must initialize again. Okay, I will stop here and I just want to confirm that everything is all right or not. So you can see velocity profile has been applied in a proper way. So you can change the option to the simple 2D arrows and scale as 0.7. Okay, now from the contour plots you can have the better idea. Okay guys, just sorry that I applied velocity profile in the wrong field. So this should be applied over here. So this is the velocity profile for the channel. So apply and run calculation again. So I was not getting the proper velocity vectors at the inlet. Okay, now this should make the things correct. Okay, so now from the velocity vectors, this is now perfectly all right. Okay, this is a parabolic velocity profile from the very beginning. And the same thing I can see in the contour plots. Yes, this is what I wanted here. Okay, you can run for the few more iterations, and meanwhile, we can discuss the velocity profile. So velocity profile says that okay, so the first thing is that this is the same as for the pipe velocity profile. So this is the y minimum is 0. This is the y maximum is the 0.05. That is the height of the channel. And the mean velocity or the average velocity is 1 meter per second. This is the definition defining the profile. And this is the definition or the macro for defining the loop for getting data over the all the cells. So cells means this is the one cell, this second cell, third, fourth. There are around 19 cells because we defined the 20 nodes, so it makes 19 cells. So for all cells, it will apply this thing here. So this is the velocity profile is u is equal to u maximum is 6 times u mean. It's not a perfect definition to define the u maximum. You know, u maximum is not this. The u maximum is 3/2 of u mean, but you know this extra term is on this side is a 4. So that's why to make the thing simple, I just made it u maximum is equal to 6 times of u mean. But actually this is different thing. Okay, so this is 6 u mean, and then we have the y by h minus y by h whole square. Okay, so this is the velocity profile which we are applying here. So when you model the half channel, means that when there is a free stream on the top side here. So in that case, you have to only add this thing here in the velocity profile over here. So you have to add one more bracket. So this will be the like y upon bracket 2 times h Or you can do one more thing, that you can define the y maximum as here, because this is multiplied by the h. So you can make it like y maximum as so y is equal to 2 times multiply sign like this, then bracket y max minus y minimum. So there's no need to change the UDF equation here. So just change the things over here. This will solve your problem. In this way, you can apply the velocity profile for the open channel. So only make the simple change over here. That's a simple thing here. Okay, now come back to our solution. So again, we can plot the XY plot, but for that we have to have so you can do it on the inlet outlet first. So make it 0 and the 1 position on the y-axis, and we are going to show the x velocity, and this is on the first inlet. So this is giving you the parabolic velocity profile. You can also export this velocity profile into Excel, like you can write the XY file from here. Okay, so in that case you can export for the Excel, or you can also use the Origin Pro. It will give you the better graphics. Okay, so now you can have the lines here. Okay, like this, and you can also change your axis. So on the y-axis you can make it like from 0 to 0.05. Okay. And on the bottom axis you can make it from 0 to 1.6. This will give you the even division of your axis. So you can make it maximum to 1.6. Okay, so this will give you the 0, 0.2, 0.6, and you can also plot them in this way also. You can plot the lines also. So also for y-axis. And for the y-axis, I would recommend that you can also make it like 0.06. Okay. So, and also you can make it float and apply. So you know this is exactly at the 0.05. Okay. So this is a velocity profile for the channel, closed channel, and previous case was the velocity profile for the pipe. So in this way, we completed this complete workshop where we derived the velocity profiles from the very scratch, like these 3 profiles. Then we applied them on 2 cases, velocity profile in the pipe. We confirm the solution, we confirm the results also in this way and also in this way. So I hope that this will clarify some concepts in applying the velocity profile, why we need them, how to apply them, how to compile the UDF. And this is not a very detailed course on UDF, but it should help you to start your understanding in the UDF. Okay, thank you very much for watching this video, and see you next time.